So in porous media flow, so far we have seen some basics where we started talking about porosity, permeability, Darcy's law, advection diffusion equation, etc. Right? And after considering advection diffusion equation, we also tried to see the mixing behavior in porous media. So we saw two different kind of mixing, one with purely with molecular diffusion and other one with mechanical dispersion, where in a molecular diffusion we consider there is absolutely no flow and mixing between contaminated fluid and the fresh fluid is happening just because of diffusion, whereas when there is a background flow in the water, then that background flow actually enhances the rate of mixing, and that mixing we call mechanical dispersion. And we have seen both the cases, but in case of mechanical dispersion we considered the velocity to be uniform, right, it to be constant everywhere, so that we did not consider the effects of changing velocity, and we only used the advection dispersion equation to model our mixing behavior. But what happens is, it's not always that the velocity is constant. Many times the background velocity is zero, but the injected fluid creates velocity for itself. So if you consider this example here, there is some contaminant release into the groundwater, right, and there is a, let's assume that there is continuous release of the contaminant. So this contaminant fluid has higher concentration than the ambient water, and then that's why this actually tries to go down on its own, while we assume that there is zero velocity here for the ambient fluid. So if it doesn't matter whether it has zero velocity or background velocity, but this plume that comes down, that is forming, that will have its own velocity. Why? Because it is denser than the ambient fluid first, and also there is continuous injection. So there is basically continuous fluid coming from the source into the plume, right? And we assume there is this gravity effect downward, so that will drive the flow. And in these kind of cases, the flow that is developed is called plumes, as you can see, and it can also be named as the convection in porous media. Convection from an isolated source. Okay, because this is basically convection. What is convection? The flow that develops because of density difference, right? And here the density difference is coming because of the concentration difference. So there is this delta C that is driving, that is resulting in delta rho, and that resulting delta rho is actually creating plume. Okay, so this is something we are going to see in today's lecture. And what you see here in the right hand side is an experimental image where we are injecting a dense fluid with a rate Q. So that is, let's say, volume flux, and it has a density of rho naught, which is greater than rho infinity, and rho infinity is the ambient density here. Okay, so it is denser than the ambient density, so it must be going down. And as a result of rho naught, there is a concentration, let's say C naught, which is greater than C naught is greater than C and infinity, and we'll assume that C infinity here is 0. Okay, so in these kind of cases, now you can see how this continuous release of dense fluid is actually creating a plume downward. Okay, and we assume that this is placed vertically downward, so there is an effect of gravity here. Okay, so gravity is acting downward, and that's why there is this plume that is created in downward direction. And now we will see the dynamics of this plume, what exactly is happening here, and we will try to derive a theoretical model. All right, and the theoretical model we derive here can be actually applied to actual plumes, as you see sort of an example here. So before we go, we will make some assumptions, some important assumptions. So assumption 1 is plume is fully developed such that it is long and thin, and that its early dynamics can be neglected. All right, so what we are assuming here is that we started injecting this dense fluid here. So it has, the moment it started injecting, uh, it has already been long since it started, so it has been flowing for a long time, right? And if it is flowing for a long time, what happens is plume is fully developed, so it has already become very long and thin in shape. So this is generally what you see for a plume which is kind of running for a long time. It will generally be very long in the vertical direction and thin in the horizontal direction, right? So in these kind of cases, we can assume the plume to be fully developed, and then we don't have to worry about what happens when the flow just begun. So we assume that this is a late time plume. Okay, so this will make our theoretical formulation easier, and that's why we are assuming this. Okay, and then we assume that injection at the source is continuous such that Q is constant. So we will call it Q naught here instead of just calling Q. So that is Q naught, this is Q naught. So here it is Q naught, that is the volume flux. Okay. So constant in time, and we are solving for two-dimensional system. So we assume the third dimension to be of unit depth. So we will consider y to be equal to 1. So consider that this is your z-axis, this is your x-axis, and then y is in third direction, and that we are considering to be equal to 1. So we don't worry about what happens in y. So flow is symmetric across the depth. Okay, and then fourth is ambient fluid is static. So u is equal to 0 for or we can call u is equal to 0 for the ambient fluid. Okay, so there is basically no background velocity. So no background flow. Okay, and then fifth is that ambient concentration is 0. So C is equal to 0 outside plume. All right, so these are some assumptions for which we are trying to model the plume problem. Okay, so now let's look into the physics of the plume before we model it, or before we try to define some governing equations and boundary conditions. So here we are assuming that this is coming in with a rate Q naught, right? And it has a concentration of C naught and density of rho naught. Okay, where concentration is obviously greater than, so C here is equal to 0, and rho naught is greater than rho infinity, where this is rho infinity. Okay, so now when plume actually is going down, it continuously mixes with the ambient. So what happens is there is a concentration difference between the plume and the ambient. So there is a delta C that actually results into this dispersion of the ambient fluid into the plume, right? So there is a continuous mixing between the plume and the ambient fluid, and that is why this volume flux that you see, which started with this Q naught, that actually as you go down, somewhere here. If you define it as q of z, this q of z at any location will be greater than q naught, right? Because there is an additional volume coming from the ambient into the plume. Okay, and now because there is mixing from the ambient into the plume, there will be dilution, right? It will get, plume will get diluted as it flows downward, and that is why the concentration at any location c of z will be smaller than c naught, or rho of z will be also smaller than rho naught. So this happens because of mixing from the ambient to the plume, right? So mixing from ambient or between ambient and the plume result into increase of volume flux and decrease of concentration. Okay, so this basically increases volume flux and decreases concentration and density, right? And we call this term as transverse mixing because it is happening in transverse direction. So majority of the flow is happening in vertical direction, that is the longitudinal direction, right? But the mixing happens in the transverse direction. And why exactly is that happening? Because as we considered here, the plume is long and thin, right? That means your vertical length scale, your z is much greater than x, right? If z is much greater than x, then your dc by dx will be greater than dc by dz, and du by dx will be greater than du by dz. So your concentration gradient in the transverse direction is much more than the vertical direction, and that is why the mixing actually or entrainment happens from only in the horizontal direction, because this concentration particularly is much more than concentration in dc by dz direction, right? And that is because this plume is long and thin. Your vertical length scale is much greater than horizontal length scale, where horizontal length scale is very thin, right? And that is why this particular condition holds, and if this condition holds, then mixing must happen in horizontal direction, not in vertical direction. All right, so now we have considered most of the basics of the plumes and how does it evolve. So we can now try to find the governing equation that will be useful for solving this problem. So we will start with du continuity equation, which is written as du by dx dw by dz equal to 0. And remember, we are solving for two-dimensional flow, so we don't worry about the y component. And then u will be minus k over mu dp by dx, and w will be minus k over mu dp by dz minus rho g. And this is because your z is downward, okay, and g is also downward. So these two minus signs we have here, that makes your g to be positive in z direction. So in previous cases we considered z upward, but here we considered z to be downward, and that's why g and z, or z and g, are both in the same direction, and that's why we are able to write this equation. And then we will write advection dispersion equation as dz okay. So this is the advection dispersion equation, and we can write density as beta delta c, okay, where beta is the solute contraction coefficient, okay. And if C is equal to 0 for the ambient, then we can simply write rho to be rho infinity 1 plus beta C, where C here is the Plume concentration. Okay, so this particular equation is for C equal to 0 for the ambient, so delta C basically becomes C. All right, so what do you see in these equations? This set of equations are, this is the continuity equation, that is basically the mass balance, and these two equations are the Darcy equation or Darcy's law, right? This one and that one, which is one in horizontal direction and other one is in the vertical direction, and this equation is the advection dispersion equation, right? And this is the equation of state. All right, so we have equation 1, then let's say equation 2, equation 3, equation 4 and equation 5. So we are using total 5 different equations to solve this problem. Okay, so for Darcy's law we have 2 equations because we are considering 2 directions, and we don't worry about the third dimension. And in case of advection dispersion equation as well, we have not considered the y term. Okay, and at the same time, as we know that dc by dx is greater than dc by dz, or in fact I will say it's much greater than that. So dc by dx is much greater than dc by dz. This value dc by dz should be equal to 0, because that is much smaller compared to d square c by dx square. Okay, so this makes our problem more simplified. At the same time, in this term, you see, again, you might argue that dc by dx is greater than dc by dz, so we should neglect dc by dz, but in that case, u is actually greater than w. So here, while du by dx is greater than du by dz, but u itself is actually smaller than w. So we are assuming this to be w, this to be u, which is in x, and w is in z. So u is smaller than w. So in this case, u is smaller, but dc by dx is greater than dc by dz. Okay, so in the left hand side term, it is difficult to avoid one over the other, and that's why we retain both the terms, whereas in case of right hand side, we are able to simply neglect one of the terms. Okay, so now if we consider this set of equations, and we will use some initial and boundary conditions before we try to find a solution. So initial condition says that C is equal to 0 everywhere before the flow began. Okay, so that is very straightforward, but then boundary condition say that, and we are defining this as z, this as x. So at z equal to 0, you have q volume flux, q is equal to q naught, that is the volume flux. Okay, and we define these as meter square per second because we are not worried about the third dimension. We are considering this to be per unit length in the third dimension. Okay, and c equal to c naught and rho is equal to rho naught. Okay, at z equal to 0 and at x tends to infinity. Okay, so that is the far field condition, much far from the center line. So if you go to this side, your C is always equal to 0, right? So anywhere near Z equal to 0, C cannot be equal to 0, right? Because uh, that is now the plume, but we are not able to define where is the plume ending, and that's why we say that tends to infinity is where plume ends, and there the concentration C is equal to 0. Okay, so these are few conditions we have, and one more thing we can derive from this one is Z equal to 0. We can define the buoyancy flux B naught. Okay, and if you remember, buoyancy flux is given as volume flux times reduced gravity. Okay, so this is something we defined when we talked about plumes in the free medium. So here we can define it as Q naught over G prime naught. And how can we define G prime naught? Rho naught minus rho infinity over rho infinity times G. Okay, where rho naught is something that we just defined, the source density here. So this is Q naught here, this is rho naught and C naught, whereas rho infinity here is the ambient density and C infinity is equal to 0. Okay, so rho naught is the source density and rho infinity is the ambient density, okay, which is basically the reference density for this case. So this gives us the buoyancy flux per unit depth. This is the buoyancy flux per unit depth, where by depth we mean the y-axis. Okay, and you can figure out what is the unit of B naught in this case. Okay, so now we have defined complete problem. We have the governing equations, we have the initial and boundary conditions, and we have again another boundary condition at the source, and this gives us the solution for volume flux. So these are the things that we are trying to find out: volume flux with respect to depth, then concentration and rho with respect to Z. Okay, so let's start with the volume flux. So this actually comes based on a similarity solution, so which we are not discussing because it's a very lengthy derivation. So we will not worry about the derivation, but I'll write the final formula that we get here. So Q of Z finally comes out to be 36 B naught K Z over nu 1 over 3. Okay, where B naught here is the buoyancy flux per unit depth, which we have already defined here. Okay, and K is the permeability, nu is the kinematic viscosity, which can be defined as mu over rho infinity. Okay, and Z is obviously the distance from the source, right? And that you can consider from this figure. Let's copy this. All right, so we are assuming that here is Q naught or B naught, which B naught comes from both the Q naught and rho naught is dependent on C naught. So right, so this gives you the Q as a function of Z, where Z here is measured from the top, from the point of injection. And you can see how the volume flux of the plume is increasing with 1/3 power of Z. Okay, so and we need to note that this volume flux is per unit depth. So volume flux per unit depth, and that again is the y direction. So this will give you Q in meter square per second. Okay, not in meter cube per second. All right, so now we have found out how the volume of the plume is increasing, so we can also predict the reduced gravity. Okay, and based on that we will predict the concentration. So we know that the buoyancy of a plume is conserved for zero concentration of the ambient fluid. Okay, so this is again something that we have seen in case of free plumes. If the ambient concentration is zero, okay, if C infinity is equal to zero, that means there is no additional solute molecules coming into the plume. It is just the fresh water that is coming into the plume, and that is why the buoyancy of the plume remains constant. Okay, and that is why this, while we define Q as a function of Z and rho as a function of Z, or G prime bar as a function of Z, B of Z is actually simply B naught. So B is actually constant in Z. So B remains constant in Z. Okay, that does not change. And how do we define B? B of Z should be Q of Z times G prime of Z. Okay, and here we will call it G prime bar because this is the mean reduced gravity at any Z. Okay, and why do we call it mean reduced gravity? Because this plume concentration or value, that actually, as you go from left to right, the center line will have maximum density, but it will, as you go away from the center line, the density decreases, and that is why the density of the plume is not constant at a particular Z location. It is also a function of X. It's not just a function of Z, it is function of X as well. But in our modeling, we don't want to worry about this variation. We just say that there is a let's say rho bar or G prime bar, etc. So that is the mean value. Okay, so we try to find the mean value so that we can avoid considering the variation in X direction. Okay, and in that we can write here as G prime bar is actually X as a function of X and Z both, that we find the mean value just as a function of Z. So we find the mean value in X direction. Okay, likewise rho here as a function of X and Z, but we define rho bar as a function of Z only, and concentration will also be a function of X and Z, but we'll define C bar as a function of Z only. Okay, so this variation that we have from left to right, and here we assume this is X direction, we consider this to give us a C bar value, okay, if this is a function of the x and z. All right, so now we have seen what is the mean reduced gravity, and we know that this particular equation is valid. So B of z must be equal to B naught, where B naught is the source reduced gravity, right? And that is why your Q of z, G prime bar of z must be equal to Q naught and G prime naught, where G prime naught is something we defined here, that is this term. Okay, so I'll write G prime naught as rho naught minus rho infinity over rho infinity times G, and this gives us G prime bar as a function of z equal to B naught over Q of z. Okay, and what is Q of z? That is something we just found out, that is this formula, right? And if you divide B naught by Q of z, that will give us G prime bar of z as B naught square times nu 36d k 1 over 3 z over 1 by 3. Okay, so this is your G prime bar, which is the reduced gravity, which now you can see that G prime bar is proportional to z to the power 1 by 3. So basically it is decreasing with z. And you know, if you use equation of a state, this actually gives you G prime bar to be same as G beta C. Okay, so this is the relation you will get if you use equation of a state on G prime bar, uh, uh, which is a very straightforward relation, right? Because G prime bar is defined based on delta rho, right? And delta rho is equivalent to delta C. So that gives you this relation, and if you use this will give C bar as G prime bar over G beta. So mean concentration of the plume is defined as 1 over G beta B naught square nu over 36 dk 1 over 3 over z to the power 1 by 3. Okay, so this is the mean concentration of the plume, right? And now if you use equation of a state, that will give you mean density of the plume as well as a function of z. So you can see how reduced gravity and concentration decreases with z, right? As you go away from the source, it actually decreases, and that is exactly what we also saw in this schematic, that as you go down, the volume increases here, right? But the concentration decreases because of dilution, because of mixing. Okay, and if you want to plot it in xy sorry, in this plot, so let's assume this is Q of z, this is concentration of the plume, and this is your z axis. So Q of z will actually increase with z to the power 1 by 3, right? This is Q of z, and your C bar decreases with z to the power 1 by 3. Okay, where you can consider this to be z, that is the source location. So this volume flux, as we discussed, is continuously increasing with distance from the source, and mean concentration is decreasing, right? And now you can use this formulation to predict the contamination of groundwater due to some contamination source. If you know what is the rate of discharge, let's say you have some discharge rate Q naught and C naught, etc., And if you know what is the permeability of the medium, if you know the K value, and if you know the viscosity of the fluid, etc., so you can very easily find out how much is the mixing, what is the concentration. And while I'm only presenting some final results, you can actually also find out what is the velocity, what is the thickness of the plume, and several other things from the model we have derived. Okay, so this kind of analysis is very important when we consider groundwater flow, because it tells us how much contamination could happen based on uh, some leakage at a particular source. And if you see, there are some wells. For example, this is the plume, and there is a well here, right? That's a well, this is a well. So now, based on the contamination that is happening due to this leakage, if you use this kind of model, you can actually predict what will be the concentration C here, what will be the concentration C here at this well. And based on your estimate, you can actually try to decide the depth of the well, right? Or you can actually find out how much will be the concentration of the contaminants into the groundwater, and based on that, you can figure out whether that could be safe for drinking, or for potable use or not. Okay, so with this, we conclude plumes in porous media, as well as uh, overall flow in porous media, where we have discussed both the flow part as well as the mixing part. In this particular topic, what we did today is plumes in porous media, which gets generated because of some continuous release of denser fluid. Okay, and by using this simple mathematical model, you can very easily uh, predict the amount of contamination, and also the location of the contamination, etc.